Jointer, joining flexible monitors with heterogeneous architectures. This is a joint work from universities of L'Aquila, Sassari and Cagliari. As embedded systems grow more complex, and shift toward heterogeneous architectures, understanding workload performance characteristics becomes increasingly difficult. In this regard, runtime monitoring systems can support on obtaining the desired visibility to characterize a system. This demo presents a framework that allows to develop complex heterogeneous architectures, composed of programmable processors and dedicated accelerators on FPGA, together with customizable monitoring systems, keeping under control the introduced overhead. The Multi-Dataflow Composer tool is an automated tool that takes as input a set of dataflow networks, and merges them to generate a coarse-grained reconfigurable data path. Among other features, MDC is able to generate a ready-to-use Xilinx IP that embeds the generated coarse-grained reconfigurable data path. The Adaptive Potential Hardware Profiling System, IPHS, is a library of elements to compose hardware monitoring systems for reconfigurable architectures, in order to support on the characterization of platforms from the point of view of different metrics. It brings flexibility and reusability in the usage of hardware monitoring systems by providing monitors composed of three parts. The adapter is the part interfaced with the entities controlling monitoring, and it has to be changed according to the connections adopted by such entities. The nucleus is the part that contains the logic to evaluate metrics, so it is dependent on the specific metric to be monitored. And the global monitor, GM, interface is the part that initializes and sends data to a central information collector. The Jointer framework is shown here. It is basically an integrated design flow for the development of customized monitored complex heterogeneous architectures, composed of programmable processors and dedicated accelerators on FPGA. The design flow, starting from dataflow specifications, generates heterogeneous dataflow-based coarse-grained virtual reconfigurable systems. In these heterogeneous systems, the monitors are automatically inserted at different levels in a composable way. The target architecture is a heterogeneous processor-coprocessor system. In particular, coprocessors are the Xilinx IPs automatically generated by the MDC tool. In these IPs, the accelerator is a coarse-grained reconfigurable data path. This kind of architecture can be instrumented at three different levels of monitoring. The first level monitor is able to count the number of writing and reading transactions happening on AXI4 full bus, that are within a predefined range. The AXI full bus, in this case, is adopted by accelerators to communicate with the processor. The second level monitor is able to measure the latency of the accelerator, thus the monitoring action, the nucleus, is dedicated to characterize the performance of the acceleration. The third level monitor is able to verify, at runtime, the occurrence of certain events, enforcing the monitoring action to verify the correctness of the execution. The rest of this video shows the step-by-step adoption of the Jointer framework. Step 1. Model application. Firstly, it is necessary to model applications that we want to accelerate through dataflow models. Dataflows are designed through XDF files. Dataflows have inputs, to receive data to be processed. Outputs, to give results back to the external world. Actors, that model single operations to be done within applications, and connections linking actors, inputs and outputs. Dataflows can also be hierarchical. Actors are designed in CAL, a language similar to C. In this demonstration we modeled two edge detectors, Sobel and Roberts, and we are going to combine them into the same coarse-grained reconfigurable accelerator. Step 2. Generate CGR accelerator. The CGR accelerator is generated by a ORCC run configuration execution. Such configuration requires an output folder where CGR accelerator will be located, and the MDC is backend among the ones provided by ORCC. The list of dataflow networks to be compiled and merged, in this case the modeled Sobel and Roberts edge detectors, should be inserted. For generating a CGR accelerator, the multi-dataflow HDL generation has to be selected, requiring a protocol XML file describing how dataflow actors communicate in hardware, and an HDL component library containing the hardware descriptions of the actors involved in the combined dataflow models. The protocol file basically specifies which are the signals that have to be placed in the generated CGR hardware description for each actor and for each connection within the dataflow model. The HDL component library should provide the hardware descriptions for every actor involved in the dataflow models. Such descriptions can be generated manually or with high-level synthesis tools. If an accelerator IP is generated, it is possible to decide the processor-coprocessor coupling between memory-mapped and stream, the kind of host processor between ARM and microblaze, and the adoption, or not, of a DMA. In this case, a memory-mapped CGR accelerator communicating with an ARM processor through DMA has been generated. Step 3. Analyze the generated files. The accelerator output folder has two subfolders. Accelerator contains files necessary to implement and manage the accelerator. The BD folder embedding Xilinx Vivado block design files for the accelerator. The drivers folder embedding the software drivers for accessing accelerator from the host processor. The HDL folder embedding the accelerator hardware description files. A report.txt file where information about the dataflow models combination, such as number of shared actors or SPOCs, performed by MDC. The script subfolder in the accelerator generation output folder provides scripts to easily and quickly use the system in the practice. The generate_ip.tcl script is in charge of generating the accelerator Xilinx IP. The generate_top.tcl script is in charge of generating the integrated processor-coprocessor system. Step 4. Accelerator IP and system generation. The scripts provided by MDC can be processed by the Xilinx Vivado environment. In order to perform this step, is then necessary to have such tool available in the adopted machine. Firstly, it is necessary to set as current folder the accelerator output folder. Then it is possible to launch the accelerator Xilinx IP generation with the generate_ip.tcl script. This script creates a new Vivado project where the accelerator is assembled starting from the files in the accelerator subfolder. Once assembled, the accelerator is packed into a ready-to-use Xilinx IP. At this point, the integrated processor-coprocessor system can be generated with the generate_top.tcl script. This script creates a new Vivado project where the accelerator IP is instantiated, together with the selected host processor and the necessary communication infrastructure. The system is assembled through the Vivado block design feature and the process takes about 1 minute. In the block design, all the integrated system components are shown: ARM host processor, system bus, DMA engine, and accelerator. The provided software drivers can be used to easily offload computation to the CGR accelerator. They basically provide one different function call for each accelerated functionality, corresponding to each input dataflow model, transparently managing data transfer and accelerator configuration to the user. We start from the Vivado project generated by MDC. This is the resulting block diagram. Now suppose that our goals are to monitor the latency of the accelerator on doing Sobel filtering, and to perform a runtime verification of the actual runtime transitions happening inside the accelerator hardware. The connection between the accelerator and the CDMA represents the place where we should introduce the hardware monitoring system. Let's use Jointer to automatically introduce the monitoring system inside our hardware. The first action is to close the Vivado tool and move with the shell in the folder where we have the downloaded Python script, the project folder, and a text file with a list of libraries requirements. Let's first install the requirements using pip package manager. Now launch the script. A folder with source files will be automatically downloaded from a repository the first time. A user interface will appear. Select the hardware project to which the monitoring system should be connected. In this case, it is the Sobel/Roberts accelerator. Select the level of the monitoring system to introduce in the hardware design. The second level monitors the latency, while the third level performs a runtime verification. The first level measures the number of bytes effectively processed by the accelerator, but we are not interested to it for now. Press Generate to obtain the monitored project. A new folder, named project_monitored, will be created, and Vivado will be automatically opened at the end of the process. Let's see in detail the resulting project. A sniffer, representing the monitoring system, has been added to the hardware. The execution of Sobel filtering is done on a Zinc 7000 on a Z-board. The execution provides a filtered image as output. We can see the filtered Lena image here. The monitoring system provides the necessary information as output as well. They can be obtained by using the provided APIs. As required, the latency of the acceleration, namely, the second level result, and the runtime measure of internal transitions, namely, the third level result, constitute the monitoring results.